In this video lecture, let's talk about whether it is a good idea to use a recursive method to solve a problem, assuming the problem could be formulated recursively, going by the base case condition, smaller case conditions, as well as the generalization. Recursion, even though it looks different from iteration, they are interchangeable. Let's not talk about the pros and cons yet. Every recursion could be turned into an iteration and vice versa. This means if you have a iteration, it could be formulated into a recursion. Recursion can be formulated back into iteration. So this is a top-down, bottom-up thing that we're talking about. So let's talk about a couple of factors and whether using recursion is a good idea or not. Right? The pros and the cons. When solution is good, it has to be efficient. Efficient means time and space. Is it going to be faster or is it going to be less memory consumptive? From the perspective of space, you don't want to have a bulky solutions out there. Meaning, if the solution takes up a lot of memory space by design, by extension, that solution is a lot slower than, let's say, a solution that is linear. Time and space are typically related to each other, so there's dependencies on each other. What is the problem? What is the overhead associated with recursion? Recursion uses a lot of stack memory. This is the activation frame in computer science. If you take hardware engineering, they typically go through these things. This is also what we call stack memory. The stack is very small. If you look at a memory chip, it's logically partitions into different areas. So this is a heap. There's a stack memory right here. There's also a data frame, and there's another one called text, and there's another one called BSS, right? So I won't get into too much of it because some of these locations are meant for different things. Like, for example, all of your static or uninitialized variables get stored in the data or text section of it. There's different logical partitions in memory that host these informations. We're talking about stack here, which is this one, and also heap. The reason why this is called stack is just because that's how memory is stored. Last in, first out. When recursion calls a recursive call, every single one of this call is stacked up against each other. This allows your flow control to go back. It knows where to go back. There is a trail or backtracking feature associated with the stack. The problem is the stack memory is limited. You don't want to keep calling it. It's like a budget. You're given this set budget to compute. This budget is going to run out at the end of the recursion or recursive calls. Eventually, that's going to be the cost to you. The worst case is that the program is going to shut down. This is pretty inefficient. If you have an algorithm that has a pretty large amount of recursive calls, you do not want to use that. If this recursion calls a lot of data structures for storage purposes, then all of a sudden you're going to run out of it. At some point, more and more expensive to the extent just cost prohibitive to have this run at one time. And there's two business requirement tied to it. This is what we meant by SLA, the service level agreement, meaning this computing solution has to be turned to the caller within due time, within 2 milliseconds, within 1 nanosecond, right? Whatever that SLA is. So yeah, you don't want inefficient algorithms manifested in this recursion that just goes on and on and on with limitations all over the places, not like a solution in general. Lots of time recursion is used when, let's say, the problem space is not that big, meaning the stack frame or the activation record inside your stack. It's not going to grow into infinity. Okay. So if you have this thing that goes into infinity, this is the infinity sign. That's not a good recursive solution. Let's say your stack frame is limited and you know that this solution is always going to be from here to here. And this is maybe like 20% of your stack or 30%. So this is your stack frame, which is the same as activation record. Stack or activation frame as part of your dynamic memory management. Assuming you have a data structure that's not going to require infinite growth in the activation frame, a recursive solution usually is a lot simpler to read. If you look at these recursion methods, especially trees, you can do depth first search. You can also do breadth first search. So these are traversal mechanisms that could be easily expressed for simplicity and also clarity in a recursive way. This is much easier to write and also understand than writing iteration methods. Non-recursive approaches typically means iterations. One is top-down, one is bottom-up. For clarity's sake, if your stack memory is not going to be as huge, meaning that you can control the amount of depth, right, this recursion goes into, recursion could be a good solution approach. Otherwise, you go with the iterations. But that's basically what I wanted to talk about from a trade-off standpoint.